In this class, we will enter into the second module of AMNOT. Second module consists of inner product, length and orthogonality, orthogonal sets, etc. So we will discuss inner product. What do you mean by inner product, length and orthogonality? The overview of this module is like this. Yes, you know the geometric concepts of length, distance and perpendicularity in the case of which are defined for a 2D space, 3D and 3D space, that is which is having xy axis as well as xyz axis. So you know the length of a vector, distance between 2 points in that space R2 or R3, and perpendicularity of two vectors. Now we are in this module, we are going to extend these concepts to in a generalized manner, that is to Rn. Okay. Now inner product. What do you mean by inner product? Inner product is defined for two vectors u and v. If u and v are vectors, two vectors in Rn in general, then we regard u and v as n by 1 matrices. That means it will have n rows and one column. That means while we are defining vectors, we have discussed this n by 1 matrices. The transpose u transpose will be 1 by n matrix, and the matrix product u transpose v is a 1 by 1 matrix. That is, it is the result of u transpose v will be a scalar number, a real number, which we write as a single real number or a scalar number without brackets. The number u transpose v is called the inner product of u and v. So the inner product of u and v is defined as u transpose v. And often it is written as u dot v. U a point and v, and we call it as u dot v. This inner product mentioned in the dot product. Inner product is also known as dot product. U dot v. And is let us take up an example where u is equal to u1, u2, etc. un, which is an n by 1 matrix. V is equal to v1, v2, etc. vn, again n by 1 matrix, and the inner product of u and v is defined as u transpose into v. Inner product u and v for dot product u and v is u dot v is equal to u transpose v. That means this is 1 by n. This will be n by 1. So that matrix multiplication will result in a single real number, a scalar. Suppose this is equal to some c, belongs to the real number, set of all real numbers. So this is what you call as inner product. Now we are taking an example of inner product, that is, we have two vectors. The examiner given two vectors u dot v and u and v. They have given 2 minus 5 minus 1 is equal to 3, 2 minus 3, and this u belongs to R3 and this v belongs to R3, and u dot v and v dot u have to find out. So u dot v is u transpose v and you will get -1, which belongs to the set of a real number, which is a scalar. Yes, then v dot u is v transpose u, and again this -1 again belongs to real number. So our then that example, the conclusion of the example 1 is that theorem 1. Let u, v and w be vectors in Rn, and let C be a scalar. Then yes, you have to imagine these u, v and w vectors. Right, vectors means already we have discussed, so no further discussion, nothing. So A, the first u dot v will be equal to v dot u. That is what we have proved in example 1. U dot v equal to v dot u. Okay, then that is what you call as yes. Then u plus v dot w equal to u dot w plus v dot w. Your commutative law. And cu dot v equal to c into uv. Yes, all these are the properties of inner product. Okay, you can take up the scalar constant outside, and you can carry out this u dot v product u dot v, and or you can do it in this manner. And u dot u is greater than or equal to 0. That means u dot u will be equal to u transpose into u. That means u1, u2, etc. un. Okay, this is u. So u transpose means this u1, okay, u2, etc. un. So if you multiply this, that you will get row, column, element wise product and sum. Yes, row, column, as element wise product and sum, you will get u1 square plus u2 square plus u3 square plus etc. plus un square, where u1, u2, u3 are all these are real numbers, so you will get it as a real number. Some C belongs to real number, set of all real numbers, and that too, this u1 square, if you square real numbers, positive becomes positive, negative becomes negative again. So you will get a positive value which is greater than or equal to 0. That is what this D property is written. Okay, and yes, and u dot u equal to 0 if and only if u is equal to 0. Yes, this is also can be proved. Okay, then properties B and C. Properties B and C can be combined several times to produce the following useful rule. That is C1 U1 plus etc. plus CP UP dot W is equal to C1. Okay, C1 U1 dot W plus C2 U2 dot W plus etc. CP UP dot W. Okay, that means W is inner product with the u1, u2, etc. up, and it is multiplied each term and sum is obtained. Okay. Now, yes, the length of a vector. So inner product of two vectors, that is over. Hope you understand it well. And if you have any doubts, you can ask. The next is length of a vector. Now, length of a vector means let us consider this length of a vector defined in R2 and R3. Length of a vector defined in R2. That means this is R2 and we have x and y axis and have a point P, A, B. This point P is a vector, right? So P is equal to P is a vector A, B. And if we join this origin O is again a vector 0, 0, that means 0 vector. So if you join these 2 points, 2 vectors, you will get another vector or length. So this is the length L of the vector P. Length of the vector P. So this can be extended to R3 also. So in our lower classes or plus 1 plus 2 classes, you have studied this, the length of this vector as under root a minus 0 square plus b minus 0 square, that's equal to under root a square plus b square. So this is root of a square plus b square. This is the length. So I'm extending this, you can extend this discussion to R3, R4, R5, etc. up to Rn also. Now our point is, our discussion is this, the length of the vector where the vector is in Rn, generalizing here. With n-raised v1, v2, etc. vn, then square root of v dot v is defined. Square root of v dot v. V dot v means inner product of v and v. Inner product of v and v. That's equal to v transpose v. And its square root can be defined. Why? Because it's a inner product of v and v, that is v dot v, will be a real number which is greater than or equal to 0. So square root is defined for it. So yes, and defined because v dot v is non-negative. Okay, now we are defining the length, or length is also for a mathematics student, for a mathematician, the length is known as norm of a vector. Length of a vector means norm of a vector. So length or norm of vector v, the non-negative scalar non-negative scalar, which is written as like this, 2 vertical lines, again 2 vertical lines. This is modulus v, right? But norm v means the again 2 lines will be there. So this is norm v. Okay, norm v defined by yes, from the inner product v dot v. V dot v is the inner product and square root of that. That is what you call it as the norm of vector v. That means v transpose v is v dot v, and square root of that is the norm v. For norm v, or you can say it, the length of that vector. And norm v square, if you square it, then you will get v dot v inner product. Inner product v dot v. So that's the yes. That is the length of a vector which belongs to the space Rn. Okay. Yes. Now, uh, now I'm going to define is the same vector, a vector whose length is 1. Whose length is 1. That means a vector whose norm, a vector suppose it is v, and whose norm is norm v, that's equal to norm v is under root v dot v dot v, that's equal to under root 1, that's equal to 1. So if the vector satisfies this, then the length of vector is said to be 1. So it is called a unit vector. Unit vector. So unit vector in R2, R3, you have you have been dealing with the unit vectors associated with R2 and R3. That is I and j. Then if R3 is there, then I, j, and k will be there. So these are the unit vectors. So if we divide, okay, if we divide a non-zero vector v, a non-zero vector, that means the vector we have, and whose entries are not all zeros, not all zeros. So a non-zero vector, not all zeros. That means v is not a null vector. Is not a null zero vector. So a non-zero vector v by its length, that means if we divide a non-zero vector, okay, non-zero vector v by its length means norm v, v by norm v, norm v is equal to the unit vector v, because the length of u is 1 by norm v, norm v into norm v. So equal to 1. The process, yes, and this process, the process of creating u, that is unit vector from v, is called as normalizing v. Okay, and we say that u is in the same direction as v. Okay, so next is our example, and our example vector is vector v is in 1 minus 2 2 0, which belongs to R4. So the examiner is asking to find a unit vector u in the same direction as v. That means examiner is asking to find out norm v, and v divided by norm is our unit vector. So yes, here length of v is norm v, length of v is norm v, but norm v is equal to under root v dot v, but norm v square equal to v dot v. That means inner product of v and v. That means v transpose into v. So v transpose into v will be yes, like this. That means v transpose. That means v transpose is 1 minus 2 2 0, 1 minus 2 2 0 into 1 minus 2 2 0. Draw column, eliminate product and sum, we will get 9. Norm v square. So the length is root 9, that's equal to 3. Yes. Then multiply v by norm v. That means 1 by 3 is multiplied. So what you can take is 1 by 3 minus 2 by 3, 2 by 3, and this is our unit vector u. Okay. So this is our example. Hope you understood. Then yes. Now for u and v in Rn, another definition for u and v in Rn, u and v are two vectors which belongs to Rn. The distance between u and v written as distance of uv is the length of the vector u minus v. That is, Distance uv is norm u minus v. Length means norm. Length is equal to norm. Length of a vector equal to norm of a vector. That means we have for r we have in our space 3D space we have 3D space x y z. We have a point, for example p we have, and this is x1 y1 z1 vector, and q is another vector, and its coordinates are 2 y2 and z2. So the length is the distance, that means distance between q and p is like this. So you will get, yes, that means x1 at minus x2, okay, whole square plus y1 minus y2 whole square plus z1 minus z2 whole square under root. Right, this is again defined as the norm. That means x1 minus x2 is what you call it as, and y1 minus y2, all these, this is the length, or okay, distance d is equal to distance between p and q, two vectors. This is defined for r3. So the in this discussion we are saying that you can extend this concept to rn. How you can extend? You can distance between u and v is defined as norm u minus v. Okay, then norm u minus v means actually we will compute u minus v, norm u minus v whole square, and take its square root. Norm u minus v whole square means u minus v inner product u minus v. That means u minus v transpose into u minus v. That means for R3 you have u minus v means p minus q, that's equal to x1 minus x2, y1 minus y2, and z1 minus z2 you have. So its transpose means x1 minus x2 first element, y1 minus y2 second element, z1 minus z2 third element as matrix, then into a column matrix again. Whose entries are x1 minus x2 again, y1 minus y2 again, z1 minus z2 again. So you carry out this matrix multiplication, row column element is product and sum, then x1 minus x2 whole square plus y1 minus y2 whole y1 minus y2 whole square plus z1 minus z2 whole square. Yes, this is what you call it as norm u minus v for whole square, and take its square root, that then you will get this distance d. So that is defined, that is proved for a R3 vector. So this the definition is saying that this can be extended to Rn vector, where Rn vector u and v also. So that is our definition. Now moving on to the orthogonal vectors. Orthogonal vectors. What do you mean by orthogonality? So you know in your vector calculus, which you have studied in your beta class, you know orthogonality of two vectors. Two vectors are said to be orthogonal, then it's for example u is a vector, v is another vector, and u and v are said to be orthogonal, then u dot v is equal to 0. So that is what you have studied in your beta class. So that it's the same we are proving to Rn here. Okay. So in order to prove that, we will take up an R2 vector, a vector in R2, that is v and u. Two vectors we are taking up. We are considering two vectors v and u like this, v and u, which are perpendicular to each other. Okay. This is u and this is v, two vectors, and okay, and this is minus v, right? This is uv, and this is under root, okay, norm u minus v, norm u minus v, yes, the distance between u and v. Sorry, this is the distance between v and u, that is norm u minus v, and this is norm u minus v. That means it will be equal to norm u plus v. So if these two vectors u and v are said to be orthogonal, that is, this is 90 degree. 90 degree means this should be 90 degree, and this norm u minus v must be equal to norm u plus v. These must be equal. So this has to be, if this is proved, okay, then I can say u and v are orthogonal. Okay. Now we are taking this distance between. First of all, we are taking the distance between u and minus v square. The square of the distance between u and minus v. U here, minus v here. So that means u and distance between distance between u comma minus v, that will be that is square. That will be distance between u and minus v will be norm u minus u plus v. So distance between u and v square means norm u plus v whole square. Right, u here, norm u minus v whole square, that's equal to u plus v, norm u plus v whole square. So now what is norm u plus v whole square? Norm u plus v whole square means, that means it is like some u plus v, we can say it is some w. So norm w square means w inner product w. So here we will get u plus v, okay, inner product u plus v. This is our norm u plus v whole square. Norm u plus v whole square. Now I am applying the property of inner product, that is u plus v dot u plus v means you can apply this commutative law like u dot, yes, u dot s here, u plus v dot u plus v equal to u dot u plus v plus v dot u plus v. So yes, and that's equal to u dot u plus u dot v plus v dot u plus v dot v. That means u dot u means norm 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 u square, right? Norm u square, yes, norm u square, and plus v dot v means norm v square, plus 2 u dot v. Why? Because u dot v, u inner product v is same as v inner product u by the property of inner product. So you will get like this. So this is what distance between u and minus v. Distance between u and minus v. U and minus v. This is the distance between u and minus v. So you keep that in your mind, and now we are going to find out the distance between u and v. So if this if the distance between u and v equals to distance between u and minus v, then yes, the u and v are said to be orthogonal as per as per your figure, right? So next I'm going to find distance between u and v. That means distance between u and v is equal to norm u minus v. That's equal to yes, u minus v. Now yes, same calculation. So I will get this u minus v. I'm taking norm u minus v, distance uv. We have earlier we have calculated, that means previously we have calculated distance between u and minus v square. So either you have to prove distance between u and minus v equal to distance between u and minus v equal to distance between u and v, or square of that distance are equal. Okay, both methods are true, are right only. So we are taking its square here. So that means norm u minus v square. Okay, that means norm u minus v square means u minus v inner product u minus v. Okay, now let's say will be equal to u inner product u minus v minus v inner product u minus v. That's equal to u inner product u minus u inner product v minus v inner product u plus v inner product v. That means that's equal to u square. U dot u means u inner product u means norm u square minus 2 u dot v plus norm v square. right? Because u inner product u means u transpose u, and yes, that is nothing but norm u square. Similarly, v also. Okay, yes. Now we are saying that this is, let us say this, let us name it as equation 2, and the previous equation is this distance. This is I'm naming it as equation number 1. So as you can see in this figure, if u and v are perpendicular, means norm u minus v, okay, and that means this distance between u and v and distance between u and minus v should be equal, or their square must be equal. That means one equation 1 equal to 2. That means norm u square plus norm v square, norm v square plus 2u inner product v must be equal to norm u square plus norm v square minus 2u dot v. So these are equal means cancelling this and this. That means 2u dot v must be equal to minus 2u dot v. That means u inner product v is equal to 0. The only way possible so that these 2 into u dot u inner product v equal to minus 2 into u inner product v is that u inner product v or u dot v is equal to 0. This is the only way. So we are concluding that two vectors u and v. Okay, actually this proof is based on R2, two vectors in R2. Now you can extend the same proof to Rn also, and we are defining that two vectors u and v in Rn are orthogonal to each other if and only if their inner product is equal to 0. Inner product equal to 0, that is u dot v equal to 0. U dot v equal to 0. So you have to actually you have to wonder that this u dot v equal to 0, u inner product v is equal to 0 is you have already studied in your engineering classes, BTech maths class, as well as in we are applied and this property in almost all engineering applications, right? But the meaning is if two vectors which are which belongs to Rn, not only R2, not only R3, okay, R2 or R3, it can extend up to Rn also, this property. That means two vectors u and v belongs to Rn generally. If those two vectors are said to be orthogonal vectors, then this is the actual definition that two vectors orthogonal to each other if u inner product v equal to 0. Okay, that is the. Now you can also observe that a zero vector is represented by like this. zero vector in which belongs to Rn is orthogonal to every vector in R, because inner product 0, if you inner product with any vector V, then you will get 0. That is O transpose V equal to 0. Right. So this is our another observation. Now I am extending my discussion to the very proof, the proof of your Pythagoras theorem. How Pythagoras arrived his Pythagoras theorem. Okay, that's the beauty of this inner product and yes, this distance between two vectors. Yes, let us prove that. So that let me consider this again our discussion, that here I have this distance u minus v whole square, right? That means norm u plus v whole square, right? This my now I have proved that if two vectors are orthogonal to each other, then I have the inner product of two vectors u dot v equal to 0, and that means this is equal to 0. That means you have this, and also in yes, we have norm u minus v, okay, square is equal to norm u square plus norm v square. Or you can say that from previous equation, that is equation number 1, here, from here, okay, here we have norm u plus v, okay, u plus v square equal to norm u square plus norm v square. That means yes, this hypotenuse h and this h1, let's say, and this h2. So this hypotenuse square, actually the distance, the hypotenuse square, that means you can say that this norm u plus v is this. Actually, sorry, this yes, this the norm u plus v is this, and norm u plus v is the hypotenuse h2, and norm u plus v square we have proved. So so hypotenuse square, we have hypotenuse square is equal to and this is norm u, right? Because distance, norm u means distance or the length of the vector u, and here we have norm v. Okay, so norm hypotenuse h2, and this is the length of norm minus v, that is length of the vector minus. So we have this, actually norm v, have hypotenuse square is equal to that is norm u square plus norm v square. Norm u square means norm u square plus norm v square means right angled side r square plus your this side, other side s. So this is our Pythagoras. Hypotenuse is equal to, okay, hypotenuse square is equal to, okay, that base square plus height square, base square plus height square. So this hypotenuse, sorry, this is known as the Pythagoras theorem. So this Pythagoras theorem is proved, can be proved like using the inner product. So this Pythagoras theorem can be applied to any vector, not only in R2 and R3 but also in any space Rn. Okay. So that is our conclusion.